Hello, this is the presentation for Selective Contrastive Learning for Weekly Supervised Affordance Grounding. Affordance grounding aims to localize the object part that are responsible for a specific action. So, for example, if we are given the image of knife and the action prompt cut with, the model needs to localize the blade part of the knife that is responsible for action cut with. However, acquiring dense annotation for every image is demanding. Thus, affordance grounding has been studied in weakly supervised setting, where only the multiple exocentric images are provided instead of dense annotation. During training, we rely on a set of exocentric examples and distill how the action is performed into an egocentric representation. At the test time, given only an egocentric image and the action class, the model localizes the action relevant part with class activation map. These are the examples of training set. To predict ground truth localization mask, we have egocentric image along with the action prompt at the top. And then we have exocentric images that illustrate how to perform the action with a specific object. One typical approach to address affordance grounding is to employ pre-trained backbone and fine-tune the classifier that is shared between egocentric and exocentric images. Then the class activation map for each class is used for the prediction. For the problem definition, we found that the previous works often locate unaffordable parts if they are distinguishable for specific classes, since they primarily rely on classification. For instance, in this example, since the object bicycle itself is distinguishable for the class ride, our baselines often localize the bicycle as a whole, not the parts to be interacted. And we also note that sometimes wrong parts of an object or even the background semantics are localized to distinguish certain classes. To address this challenge, we focus on directly exploring part-relevant clues from both egocentric and exocentric images. But since the identified part clues may be unreliable, which means that they are irrelevant to actual affordable parts, we only use the identified parts when deemed reliable. And when it is not deemed reliable, we instead encourage the model to stay focused on general object to prevent our model from focusing on affordance irrelevant semantics. To discover object and part clues from images, the first step is to identify the object. Simply put, we use the object affinity map from CLIP, which is the similarity between the visual features and the text features. With this object affinity map, we perform two contrastive learning. The first one is prototypical contrastive learning. Prototypical contrastive learning aims to distill the knowledge from exocentric images. To identify the affordance-relevant part clues from exocentric images, we first use the object clue from object affinity map from CLIP and CAM prediction, which is obtained during training. Then we perform k-means clustering to partition different parts. Then, since the egocentric image often exhibit only one object, we use the denotes attention map to the class token to identify the target object. And then we use this target object to find the most target relevant part in the exocentric image. In this example, since the last part among three examples exhibit the highest similarity to the target object, we use the region of last one as the part clue from the exocentric images. Then we use this part region in exocentric image as the positive target in contrastive learning. Specifically, the anchor is the object in the exocentric image, which is the averaged representation of object region identified by CAM. And the part region in exocentric image marked with blue serve as the positive target, while all the leftover patches from both egocentric and exocentric images serve the negative target. By learning to increase the similarity between the egocentric anchor identified by CAM and the gathered exocentric part clues, the model learns to focus on affordable part-relevant regions in egocentric images. However, the part clue from exocentric image may not be highly relevant to the target object. In this case, when the similarity between the exocentric target and the object in egocentric image is not high enough, we train the egocentric image to follow the object distribution in exocentric images so that the model does not deviate from focusing on affordance-relevant object. Another contrastive approach we propose is pixel contrastive learning. With this pixel contrastive learning, we aim to calibrate the fine-grained localization capability of the model. We use the property of the foundation models that they are most responsible to salient object. So, we expect stronger activations for affordable parts in egocentric images compared to their exocentric counterparts when matched with text prompt. To be specific, given the maximum value of activation on exocentric images, we use that maximum value to threshold the activations in egocentric images. And this way, we discover the affordance relevant part in egocentric representation. With this gathered clue, we perform selective contrastive learning, which is very similar to the prototypical one. First, when the part relevant pixels exist, we learn to separate the identified pixels from the background pixels. On the other hand, there are some cases when the exocentric image also exhibits the salient target object so that no part pixels can be identified in egocentric images. In this case, we instead use the object affinity map to identify the object relevant pixels and perform the pixel contrastive learning at the object level. For the experiment, we follow our baseline, locate, and WSMA to evaluate on AGD and HICO dataset. As can be observed, our selective contrastive learning exhibits state-of-the-art performances with large margins. Next is qualitative results. We compare our prediction with ground truth localization mask and the baselines. As can be seen here, we observe that our predictions are really good at localizing the affordance relevant parts. For example, our model clearly localized the head of toothbrush to perform an action brush with. For the ablation study, we sequentially studied the impact of prototypical and pixel-level contrastive learning, along with the impact of level of contrastive learning, which is part and object. Also, on the right side, we visualize how the localization results become tight as our components are sequentially added. Thank you.